Welcome to another Taz Academy HVAC training video. Today's topic, using a ductulator. Why the recommended friction setting will cause you to undersize your ducts. I am your host, Randall S. Ripley, Technical Support Manager and Trainer for Total Air Supply. There is a whole lot more to duct design than friction rate. The intent of this video is to show you why you can't use the recommended friction rate number of 0.10 to design a duct system. It is in no way intended to replace taking classes on duct design. It's recommended that you take classes and/or get a copy of the ACCA Manual D residential duct systems to get a full understanding of basic rules of duct design, do's and don'ts of duct fittings, velocity pressure's role in duct design, the equivalent length and poor performance of return bays, and much more. It's really recommended that you become comfortable with ACCA Manual D. You can download and use the Manual D speed sheet from ACCA for better results. Don't be a rule of thumber. And high performance duct systems require design, not guesswork. Today's video will focus on why you need to calculate your duct friction rate, how to calculate it using the ACCA Manual D residential duct design form, and why you can't use the recommended residential setting suggestion printed on the ductulator by the manufacturer of the ductulator. There is a whole lot more to getting your friction rate. Using the recommended residential setting is a surefire way to design a system with undersized ducts. Techs that lack equal friction rate duct design knowledge tend to use the recommended setting because it's easy and gives smaller duct sizes. HVAC projects are designed with lower friction rate, which requires larger ducts. With a low friction rate, one faulty component can severely hamper airflow because there is less room for error. And we'll get into it here shortly, but with duct systems, remember, every fitting has an equivalent length and all of that. So all of that stuff adds up, but we're going to get into that in a minute. But it's just, you have to know these things, that one error can do that. We will learn the meaning of several words you may not be familiar with, such as equivalent length, total effective length, pressure drop, available static pressure, friction rate versus static pressure. Friction rate is a value located on a ductulator. We use it during the design phase of a duct system to decide the diameter and shape of the ductwork you can use without negatively impacting optimal airflow and to predict the operating static pressure of a duct system. The techs misapply friction rate by assuming what is using a rule of thumb instead of calculating it. The rule of thumb many designers use in the field is the 0.10 inches of water column per 100 feet friction rate, marked as the recommended residential setting by the maker of the device. And you see that here. The rule of thumb becomes problematic because the actual length of the duct is not considered, which often leads to undersized ducts and low system airflow caused by excessive resistance, which is high static pressure. In order to apply friction rate properly, we need to understand its intent and its limitations. Friction rate is expressed in inches of water column. which happens to correspond to the pressure scale often used to measure static pressure in duct systems. That means they are the same thing, right? No, but they are related. Friction rate indicates how much pressure drop is allowed per 100 feet of duct system length. A higher friction rate is better, and a smaller friction rate means a larger duct is needed. Static pressure is the combined resistance to airflow of the ductwork, elbows, transitions, and hood. The Ductulator also provides another piece of information about friction rate, which is the feet per 100 feet, the friction rate per 100 feet. This means the friction rate shown on the Ductulator is based on 100 feet of straight pipe in the size selected. The challenge here is that our ducts are not all 100 feet long and they are not straight. And this is the part people tend not to read, and that's why they just go with this. That's what brings us to the terms such as equivalent length. Equivalent length given for fittings. A fitting with an equivalent length of 25 feet has an equal resistance to 25 feet of straight pipe. And the other EL, total effective length, equals the measured length from the farthest supply outlet through the equipment and to the furthest return outlet, plus the equivalent lengths of all turns and fittings. Friction rate gets calculated based on the pressure drop per 100 feet. Fittings add up quickly in a system, which means that our total effective length of a duct system is beyond 100 feet. Friction rate is the amount of resistance to airflow passing through a duct measured in inches of water column per 100 feet. When you calculate friction rate for the particular design, you're finding out how much pressure drop you can get away with for each 100 feet of effective length of your system. Friction rate is calculated by dividing the available static pressure by the total effective length and multiplying by 100. Friction rate indicates how much pressure drop is allowed per 100 feet of duct length. And there's the formula. A higher friction rate is better, and a smaller friction rate means a larger duct is needed. And if you take your duct calculator and size for like 800 CFM at 0.10 and then do it at 0.06, you'll see why people like that number 0.10 better. You will need required airflow determined by a room-by-room manual J. What equipment you're using. A hand drawing of how you're distributing the air in the rooms. It doesn't have to be anything fancy, but you just got to know your lengths and fittings and that. So, just a hand drawing is fine, but you do need that. And here you look at the location of the air handler, the distance to the ducts, how many turns the ducts have to make, and how much air needs to be delivered. The type of duct has a big impact on the results, as sheet metal ducts have a lower friction rate than flex duct or rigid fiberglass duct. But your flex duct, if it's not pulled out straight, has poor performance. Oval has very poor performance. Basically, with manual D, you're trying to balance the delivery of the correct amount of air against the friction rate of the ducts and the static pressure in the system. So now that we have that information, we can go ahead and calculate the friction rate. And again, this is just an example, guys, to show you why you just can't go with that number 1, that 0.1 recommended setting. This isn't design 101 or 105 or end all be all. It's none of that. It's just to show you why you can't use that friction rate. So we look at the form and we look at this data, and here's what people don't take into account: the available static pressure, the component pressure losses, all of that matters in this, as we're going to see. Step one, manufacturer blower data. We get the total external static pressure the unit is rated for, measured in inches of water column, and it's right on the nameplate. And then we look at our fan performance chart at the 0.05, and we see for a 3-ton AC, we need we're going to get 1,201 CFM for that. So that's the numbers that we're going to put in up here. And then you see we have components, and all these components have pressure drops. So we're going to deduct the pressure drops created by any components you plan to add to the air distribution system. Evaporator coil's pressure drop can be found in the specification sheet for the coil. Use 0.03 for the supply register, return grills, and balancing damper. That's an ACCA recommended number. So that's a 0.09 off your pressure budget right off the top. And air filter pressure drop can be found on the manufacturer's website. But just remember, there's dry ratings and wet ratings for AC coils, and it just depends on the highest one. Is it the dry rating because you need to put so much more heating air through the coil during heating season, or is the pressure drop larger during the cooling season? But you would pick the higher number. So we put the total component losses on our sheet. Then we are looking at available static pressure. So our static pressure is 0.50 minus 0.35, and it equals 0.15 inches of water column for our available static pressure. And that's because we've deducted all of these from our to get our static budget that you're working with when designing the duct system. Available static pressure impacts HVAC ductwork sizing. The less static pressure available, the larger the ducts required. You cannot exceed the available static pressure, or the system will deliver improper airflow and cause equipment problems over time. So we look over here, and we have our available static pressure now, and so we put it on our form. So step 4 is total effective length. And total effective length is the measured length of the longest supply run from the supply outlet to the plenum. The same with the return, from the side of the cabinet where the return connects all the way out to the longest run on the return side, plus the equivalent lengths of all turns and fittings. So just remember that this takeoff fitting has an equivalent length. The top takeoff over here, the plenum takeoff here has that equivalent length. The top takeoff has equivalent length. This reducer has an equivalent length. This boot here has equivalent length. Then you have all the linear feet also. So all that linear footage and the equivalent lengths, that is your total effective length. An accurate measurement is required to get proper sizing of the HVAC equipment. So just remember also that it may not be what looks like the linear footage longest run because it has fittings in there that are going to make it the highest number, and that's your longest run. Just what that total linear length and the equivalent footage of the fittings is, that's going to make the longest run. And we have actual length, equivalent length of each fitting, and that equals total effective length. And we would do that for both sides, the return and the supply. Every duct fitting and connection you use has an associated equivalent length, which is usually the forgotten thing, but it has a huge impact on design and performance. Equivalent length compares a duct fitting to what its length would be if it was straight, and it also describes the pressure loss in a duct fitting that would be comparable to a length of straight duct. Okay, so here we're talking about equivalent length. Again, duct fittings with sharp turns have higher equivalent lengths than fittings with gradual smooth turns. And this is a key thing, guys. Picking low equivalent length fittings is one of the most important things you can do for your duct design. And you see here, they all have their numbers, and you can figure out which ones you need to use. But just remember, the ones that have sharp turns and are squared off rather than rounded off and all that, they're going to be higher on your equivalent length. And if we look here at an example, I mean, this is right on the back of a ductulator. And we look at this, and this duct over here is 100 equivalent feet, and it has a square throat and a rounded heel. If we look at that same fitting, same size fitting, and it has a rounded throat and a rounded heel, we're all the way down to 20 equivalent feet. So that's why when they say it's very important to pick fittings with low equivalent feet ratings, because 100 equivalent feet for one fitting, you're going to have one hell of an effective length. Add up the effective lengths of all fittings in the longest run on the supply and add it to the length of straight sections to get the supply total effective length, and do the same on the return side. Then add the two numbers into the formula. Here you see we have, and this again, this is just a made up number, and you'll see why I made it up in a minute, but we put these numbers on our form. So now we have the tell. You're ready to calculate the friction rate. And that's total equivalent length. Our available static pressure is 0.15 inches of water column, and our total effective length is 412. If we look at the friction rate chart, the lowest acceptable friction rate is 0.06. Plotting our numbers on the friction rate chart shows us to be off the chart of acceptable friction rates. We will have to address this in some way to get back on the chart. The chart gives 3 suggestions to correct this: increase blower speed, change blower, and reduce the total effective length. So if we're already on high, and we are, and we can't change the blower, try to reduce the total effective length of the fittings. But there is one other thing we can do if none of those options are viable, and that is we can design at a higher static. And we can do that, the higher static thing, especially if we have an ECM motor, but we can also do it with a permanent split capacitor motor if we can get the correct amount of airflow. So we look at this chart, and this happens to be a permanent split capacitor motor. Yes, it will reduce the efficiency of the motor. but we don't have any choice because even on your ECM motors today, the pressure drops of these coils and stuff is insane. So we go to this 0.6, and it says that we could get 1,194 CFM at 0.06. Well, we only, so that means we've got enough airflow. So that's, we're only 6 CFM off. So we change our external static pressure to 0.60 and put the CFM at 1,194. Our available static pressure is now 0.25 inches of water column. We plot our total effective length and available static pressure, and we are just inside the minimum acceptable friction rate of 0.06 friction rate. So, I mean, yes, we will lose a little efficiency on the motor, but again, you really don't have much choice with the pressure drop that's required. But that's just a way to do it if you can't change anything else. So if you're replacing a piece of duct in the field, you're pulling out a piece to replace a piece or two because the airflow sucks there, and you look at it and you say, well, if I change a few pieces of the duct in the beginning, maybe I'll get a little more airflow down at the other end of the duct. You have to remember all the ducts in that system are sized on a calculated friction loss, or should be. But unfortunately, in a lot of cases, that friction rate is the 0.10. If you don't want to calculate the friction rate for an existing system, then use these rules of thumb to replace ductwork in the field. And again, this isn't to do a whole house. I would do the calculation sheet, if you're doing a manual D anyway. But supply number should be 0.06 or 0.07 at the most. There's literature out there that will tell you the default is 0.05, but Manual D doesn't recommend sizing duct at less than 0.06 because there's so many other things you can do if you know the rules of ductwork and all of that, air distribution and stuff. Again, this is only focusing on calculating the friction rate. But you would have to know those things. But anyway, 0.06, that's what I would go with. But, or 0.07 at the most, but, 0.06 is a safe number. And return number should be around 0.05 to cover the slower return velocity of your return. And then again, having the right amount of returns that can carry the right amount of CFM, it really matters. And that's why I say with the Manual D book, if you ever get one, read up on pan bays, and you'll see why a lot of municipalities now don't allow it. Thank you for watching the video. Hit the like button if you like the video. Please subscribe to our YouTube channel so that you can get all the videos as they come out. And there's our YouTube channel address. Thanks for watching. And there's our YouTube address again with my email. And I hope to see you at the next one.